So I did this. Kentucky Transportation Cabinet asked for a demonstration in the laboratory, and you have DOTs and Commonwealths, but they're all states, right? And so Department of Transportation. Well, Kentucky calls theirs a cabinet. So first off, that's what they're known as. They wanted an update, and they didn't want to know about the testing. They did not want to know about. They did not want to know about how to introduce it at the plant. They wanted to know. They are at the decision point of we're ready to pull the trigger. They're using 70,000 tons a year, in addition to probably 30,000 tons in Louisville, another 20,000 to 30,000 tons in Lexington. So, and those are cities. So their fiber, Kentucky may be one of the larger states outside of California that's using that much fiber right now. And so in doing it, they said, we just need to feel good and understand how it's actually working and why it's working and what's the oldest projects that you have. So I built this for them. The first intro I had, of course, was showing them a little bit about my about my laboratory. We talked a little bit about the services that we offer here. The one thing that I needed to dive on a little bit that they weren't used to was this portion here. And you're going to hear me refer to BAT vision or PCI, pavement condition index monitoring. And this is where, and I've actually got, this is actually a clickable map that I pull up on the internet that I can get to my clients. Surface Tech was one that early adopters said, Phil, please go ahead and drive our project. So I mount cameras and I drive it. And then I work with Tiger's Eye Engineering out of Missouri, and they have a AI level mapping software. Now, there's one thing to map a crack, and then there's another thing to use AI that's going to go in, and I may have a manual that I could actually demonstrate. But what that is you have distress manuals that would look at a picture like on the right, and it would say this thing going across may be a transverse or reflective crack, but when you have it breaking up into all of this is considered block cracking. You see the title up there at the top. And 0.27 represents the area. Why this on the side really represents this top box, or this bottom one is really representing alligator cracking. Block cracking is bad enough, but block cracking will have a certain severity rating and a deduct, but alligator cracking has a bigger deduct. And you start with 100 on a PCI level down to 0. But really what that means is when you drop below 80, you need to be doing 85, you need to be doing some type of maintenance on it. When you're into the 70s, you're going to have to do significant maintenance on it. When you drop into the 60s, you're going to have to do more rehab. You're probably going to be going down several, maybe 50 to 75 millimeters to rehabilitate it. And when you drop below 50 on a PCI, you're looking at remove and replace. It's too far gone. So this type of software helps us to value, and it really helps with my clients to be able to show them, is your product working or not working? Because every agency in some way uses a pavement condition index, pavement condition rating that is the trigger for overlays. The other trigger is politics, and it's very real that on the political side that can trigger a pavement overlay. But in the world of engineering, we use PCI or PCR. These are just some other capabilities that we have here that I always go over. The forensic piece is one that has gained a lot of attention lately, where we do a lot of forensic analysis, and then friction testing. So what I want to do today is really go through the suite of products, really focusing on 4 key products. And this is what's being offered by Surface Tech. So I'm going to be speaking specifically to the Surface Tech product. First thing we'll start off with is a little bit of the academic overview. When you begin to look at where we are today, one of the significant things that we have done has been able to develop an ASTM standard. And the ASTM standard is just that. It's an international standard that calls out aramid fiber for asphalt mixtures. There's aramid fiber that would be used, for instance, in the helmet ballistic industry, be used in different parts, whether you need, there's even a Kevlar type paper they have now. But Kevlar or Aramid is the generic name. Kevlar is a brand name. Aramid as a generic name, is it can be used in hot mix asphalt, but it's very specific. And so this standard calls out the key things that we need, such as tensile strength, Young's modulus, decomposition, and all of that goes into something that makes it easy for an agency to call out. It's easy to verify. I get asked a lot of times, how do you know what's in the mixture? How do you know if it's dispersing? You can begin to see the fibrils and the fibers that's in there. You're dealing with fibers, again, that's in a small sample, and in the matchstick sizes that you're looking at have 10,000 fibers in them. But when that breaks out, you're looking at 10 micron fibers that have an incredible strength in the mixture. And as long as it's into the mixture and being held by the asphalt, of course, naturally, it's going to add that strength. And as you look at these pictures, you see these fibers hanging everywhere in the mixture. So there's a lot of fibers. So it's easy to verify just by grabbing a spatula, or if you're in the field, grab a shovel and you begin to dribble it, and you'll see the fibers in it. If you really want to understand dispersion, there is a way to take it, and of course to quarter it. By quartering it, then you take and extract the asphalt out, and you can measure the amount in each one, and you should find out that it's only 0.00656% or 667%. And that's a small percentage, but that's because it's so lightweight. On the academic side, and this is just to name a few, it's been looked at improvements of rutting and cracking by Oregon State, University of California Pavement Research Center at Cal Berkeley. Angel Mateos looked at plant mix, and he looked at it in terms of modulus, fatigue, and general cracking. Butler, University of New Hampshire, you have Missouri, you have University of Alberta that looked at it in cold regions. Texas A&M did a lot of work as a polymer alternative. Florida DOT is now watching, along with other states, watching the NCAT test section. Something to note on the NCAT test track and on the test track that's in on Min Road that's being put down, the Surface Tech product was the only one that was voted to be on the track. So they were allowed to have up to 5 different products. There were 2 plastics, 1 rubber, a control, which is polymer, and the 5th one was going to be a fiber, and Surface Tech won out on that vote. Among the and voting on that were several states, including Federal Highway Administration. There's been work through University of Cincinnati, NCAT, as we just mentioned. Rowan is looking at DOD, is our abbreviation for Department of Defense. They're evaluating for extreme cold climates such as Alaska to reduce cracking. They see it as a major advancement there. And Aspahlt Institute, and then of course what we're doing here, Love's nationwide has implemented. So I'm going to talk a little bit about the implementation. Love's nationwide has implemented, and they call out the aramid fiber that goes in every project. New York, Kentucky, California, Florida, in deep evaluation as, again, a polymer alternative. We mentioned NCAT. Canada is now moving into it more and more. And I mentioned here, as far as cities, City of Louisville, City of Lexington have jumped on it. City of Louisville sees it as it instantly makes their pavements better. And so, if I had to ask them and really pin them down, they're probably getting about 5 years more life. So instead of 10 years life, they're probably getting 15 or more. If you're looking at City of Lexington, not only does it reduce cracking for them, because the roads in cities are a lot different than major highways. You can't always get them to densify, so they're prone to have crack a bit more. The other thing they're able to do is the City of Lexington recently switched over to use a significant amount of product. About 20% of their paving was replaced with a 45% high wrap mix, and that's the product that Surface Tech calls ReArm. And we're able to go in there and use fiber with a bio oil. The bio oil softens the mixture. The fiber then acts like the polymer and reinforces it. And so it's not just a recycled type of product that's being put in rural places where it never see traffic. It's going on airport access roads, major city streets, where you're not afraid of a rutting problem or cracking. And we're verifying it with balanced mix design parameters such as Hamburg and Ideal CT. I want to go through the buckets as we mention these of these different products. One again is Army, the reflective crack relief interlayer. So it's been used in some high form in the U.S. since 1998. Now that is not the fiber version. That's the high polymer version. And I put this together for Kentucky because they were not aware of all of their areas where they had used the interlayer. And the interlayer, of course, I'm referring to is the one that we can actually bend about 100 times more flexible than regular asphalt, and is designed to be low voids and designed to withstand high amounts of strain, high amounts of movement. So here are the projects that have been placed in Kentucky. The 2019 project is the first one that we put down where instead of using the high polymer, we actually used a double dose of aramid fiber to achieve similar properties and achieve the flexibility. So this was the first project in the nation and the first one in Kentucky where we substituted for the polymer and used aramid fiber to get the massive amount of resilience and crack absorption. On the Taylor County Airport specifically, and that's what you're looking at here, you can again see the fiber in the mixture. This is the inner layer that you're looking at that went down in Taylor County. And this is just a long ways looking up. As you look at this layer, you can see this is a very, very fine mix. It's 1 inch or 25 millimeters. People say quickly, well, what's going to happen when you put a roller on it? And they just know it's going to push everywhere because this has 8.5% asphalt, around 8% dust, maybe 8.5% dust. It has about 1.5% air voids, maybe 1%. And it just rolls in place, and it's going to act as close to 1 inch of rubber as you can make asphalt be. You notice the mix did not push; it just rolled into place. That mixture that you're looking at, we actually did a little bit of a study. So there's several things going on. Let's just focus on the first bar. This is one that we did for Canada. So we took the same inner layer. We used a double fiber with a very light polymer loading, and we tested at 20C, and we achieved 2127 ideal CT. That's unheard of in most places. Normally, if you receive 100 on an ideal CT, that's great. 200's great, even better. 300's outstanding, but to hit 2000, again, that's that 10x difference, the next level, and that's what we're aiming for, and that's how different this inner layer is. Well, what happens if I take my temperature down and switch the binder, or make it warmer and switch the binder? This is where we were proposing maybe an index value of 1000 or 1500, and again, we're above those. So no matter what climate that you're in, whether a really cold, a warm, or hot climate, the interlayer can be adjusted. And over here, I have, just as an example, I have a 153, which again would be considered a very good mixture. That's in a conventional mixture. 153 would exceed most specifications, double in some states. And as an example, NCAT talks about their track, and if they're seeing numbers in the 50, 60, 70, they're really happy in Alabama. Kentucky has a spec more of about 110. And then when we talk about the inner layer, again, we're looking at numbers such as 1000. Rearm is the product that I talked about earlier, is with the high wrap. And this is a dilemma. We need to use the wrap, but how do we use it? And this is a small pile, but there are piles and piles and piles, especially in metropolitan areas where they are removing it and they just don't have places to put it. Now, it's interesting that you look at nationwide stats, and you've got to scratch your head just a little bit and say, if you read the Napa magazines and you understand that these type of products are 95, and asphalt is one of the most recycled products in the world at 95%, 94 to 95%. Paper and plastic may come in there, but they're a low number. If I remember right, there's something like maybe 50 or 60% recycled. And why is that? Well, that's because you have mixed plastics, mixed glass, mixed paper. The nice thing about asphalt is that while it's mixed, it is still all coming off of highways, and it's not like we have them off of multiple sources coming off of different type of applications. They're all coming from roadways. So in having that, we're able to use this wrap. Well, now comes the dilemma of, if it's 94% recycled and we're only putting 20% back in the mix, isn't that 20% recycled and not 94? And that's because wrap can also be used as other filler materials. It's used on rural roads as an aggregate cover. And so it's used in other places just besides in the asphalt mixture. But how do we use this in the asphalt mixture, and especially on a roadway, to give us some level of confidence that it's going to perform? If you look in the US, you see numbers that are pretty flat. This is picking up from 2017. It's sort of going off the page down here. Sorry about that. But this is 2018, 19, 2020, and 2021. And if you look at these states on how they're reporting, whether it's Texas at 15 to 17, 16, 19, and 18, these are the amounts of RAP that were used throughout the state. The color coding helps you to understand the blues in the higher, the green is in the highest range of 20 to 29, whereas the black is less than 3%. I'm sorry, is lack of reporting. The yellow is 0 to 9%. So in a world that we're talking about that we need to have more recycle, that we're going to have more EPDs, how do we approach this challenge of zero carbon without using RAP? We know it's coming, but what is it going to look like? This was a study that we did, and we did this with the city of Lexington, city of Louisville. And we're going to walk through. So first thing I want to do is look at the blue bars on the left. And they said, how can we, and again, what we did this for Kentucky. Kentucky want to know, how are we using this product to solve problems? They said our current mixture that's going down in the city is about a 56 or 55.9 ideal CT, and it has a Hamburg value of about 6,000. So they said, yes, Phil, you can go ahead and design a mixture with high RAP in it. In this case, we were going to use 36%. You can design it, but we want to do that with assurance that it's not going to rut more or crack more. Also, we want to make sure it's as good as our current control that we're using with fiber. So now we raise the bar from 55.9 to 71.2 when using fiber, and from a 6198, it's still staying constant around 7,000. Normally, this number would go down. It just didn't on this one example, because that should have dropped to about 5,000. So we approached the project with the first design, and I wanted to put more asphalt in it in order to try, because sometimes the asphalt doesn't always come off the RAP. So again, in this case, now Lexington, we used 45% RAP and did the same thing here. But in Louisville, we used 36% RAP. We used a bio oil to soften the material, and the bio oil is probably around 3.5% of the virgin binder. And we also used an aramid fiber in there. So we used a bio oil and an aramid fiber. And we got an ideal CT of 88.2, which is clearly above where the city of Louisville was. And on the rutting side, it's in the range. It's not the 72 mark, but it's in the range, which was comfortable for them because it's still better. It's still better than this number and very close to this number. This is more of test error. Then we went, and this is where you got to scratch your head a little bit. We went and they wanted to build a project at 5.6. So the project ended up between these light blue bars and the gray bars. But on the gray bars, we took some asphalt out because we were a little bit too wet or too rich on this one. It dropped the 88.2 down to 69. And it raised the rutting. It should have lowered the rutting. It raised it. Again, that's just error in the Hamburg. When City of Louisville saw this and they saw that these numbers, both of these numbers, are better than where they currently were here, and better or equal to or close to or equal to where they were at this number, they said proceed. And that's why we were able to put the project down in Louisville. That's also the same reason we were able to put it down in Lexington, that we are building these high recycle RAP mixtures out of using the tools we have today, such as aramid fiber, but also giving the owner assurance that their product is going to perform as good or better than their control. That's what it looked like during construction. And I love this picture here because it lets you see the texture, and it also helps you to understand it's business as usual. They actually did it, I call the heel test. The contractor goes out and buries his heel into it, twists it around, and he said, feels like regular hot mix to me. So that was a thumbs up on that project. We also wanted to understand a little bit of an aging study, and that has come up. Kentucky wanted to understand about that too. If I use a bio oil, or I use aramid fiber, or I use different things, what happens when I begin to age that mixture? Does it age just like regular mixtures? Well, in this case, we have the CT index, and this all has the high RAP, and this has high RAP with fibers, and again, the 20% RAP. This is coming from the plant. So the plant level, when you pull it, and you begin to look at the three. This is the standard RAP that they would use. This is actually coming from the city of Lexington work, I believe. No, this is Louisville. I'm sorry. Then the blue bar here represents the RAP with the fibers, which it should go up. And this is just like what we were looking at off of the previous data. And then now we're adding in, and we're putting in the high RAP. Again, the high RAP with the fiber. We do the same thing, but now we add 4 more hours onto it. which it should about knock these in half, which it does. Now we go at 8 hours, and you expect for it to knock it down about the same amount. One thing we wanted to be sure of is when you put in the bio oil, what we didn't want to see was the bio oil drop from being a 72, for instance, down to being a 10, because that means all the light oils come out. So we want to make sure it's aging similar or better, or giving us better results than what your controls would be. And in this case, it ages like regular hot mix. If anything, the bio oils may be staying in it a bit better. And we were very pleased to see that. Again, assuring us that it's not cooking out and that it doesn't look good in just year 1, but what's it going to look like in year 3, 4, 5, 6, 7, 8. This was the Lexington project. Again, this is on Mercer, and I show you this because I'm going to take you to the roadway here in just a moment. And this is the typical control, 20% wrap with a 7622, as compared to 45% wrap that I'd mentioned, 6422, used a bio oil and a double dose of the aramid fiber. And this one, what was interesting in this one, and we actually ran through and calculated, we were looking that if this is lasting longer, not even lasting longer, just looking at the construction, so cradle to gate, just looking at the construction by using 45% wrap and a 6422 that lets us lower the plant emissions, we were looking at about a 30% reduction in CO2. That's amazing that we can do that. And maybe it's 25, maybe it's 35, but that's the number that we were calculating. This is how that mixture compacted. This is what the 45% wrap looked like when it went down. This is the aramid fiber on the wrap belt as it's going in. You can see there's a lot of wrap on that belt. And this is how it compacted. And today it's looking great. And this is what it looks like today. This is after 3 winters. There's your control, and there's your wrap. Let me give you a visual on it as we drove the roadway. Again, the left is your 45% wrap. The right is your control. Can you even tell the difference? If you look closely, the one on the left actually looks a little richer than the one on the right. Again, we're going to go over, and I'll summarize these at the end and how they're actually performing today. Valor is looking at a full depth overlay. So in 2021, we constructed this project in 2020, and then in 2021, we did falling weight deflectometer evaluation of Man o' War Boulevard. In Kentucky, we name a lot of our streets, especially in Lexington area, after horses. So you may see Ali Sheba Way, you may see Man of War, and all these are named after the famous racehorses. Man of War is what circles Lexington and feeds the airport. And if I were to look in this picture just to my right, I'm going to find the airport sitting right here. This was tear out of the concrete intersections and rebuild them with asphalt. The main line is also 10 inches thick and around 30 years old. The concern was the city said, if we tear out the 10-inch concrete intersections, are they going to rut and push, and can we go back with asphalt? The contractor and the city both came to bat and said, how can we do this and go back with asphalt and have some level of assurance? I quickly said, I've done similar with fiber. Let's do this. And I had the proof. And I said, but to make everybody feel good on this, I will do follow-ups on this every year. And we're also going to do falling weight deflectometer evaluations of this project. So not only was it built in 2020, but we went back through and continued to evaluate it annually. And in 2021, we did significant evaluation. This was the fiber machine that fed the project. Of course, nighttime work and the project it was going down. That just happened to be my son who was working for me at the time, helping with the density measurements. While I say it was a 10-inch intersection, you're looking at about a 25 centimeter or 250 millimeter in depth going down. That was put down at a 100 millimeter lift, a second 100 millimeter lift, followed by a 50 millimeter lift. So that was done in 3 lifts, 2 base and then a surface. Again, the nighttime construction. This is what that intersection looks like today. Again, absolutely beautiful, no rutting, business as usual. Here's a picture of the main line. So the main line only had 2 inches, or actually 1.5 inches that went on it, whereas you're looking at full depth. Now, we did leave a small section as a control that's being monitored with no fiber in it. So what we wanted to do, this is a falling weight deflectometer that's going to drop a weight. And I'm going to pause it there for a moment. When we let me see if I can stop it here. If you've never used a falling weight deflectometer, this is the weight that's going down with a drop that's going on. You can control the weight. These are the sensors, LVDTs, that are put out. The further you're away from the weight, the deeper we can measure, the deeper in the layer. The other thing that we do is we take cores off the projects like this to validate the layer depth. And so by going really far out, we're able to do such things as measure and understand what the subgrade looks like too. In the world of oil, you may drop these in the field, and I haven't done it, but it's several thousand feet away or even further. They have the sensors that are actually picking up and helping to understand where locations of potential oil or cave systems may be. In this case, we're only looking at a small depth, or in this case, we're probably looking at a total of about 50 to 100, maybe about 50 to 100 centimeters total depth that we're trying to evaluate. What we found out, and this picture on the left helps you understand where the main line was in the orange. The red represent the intersections. The red, the green, and the purple. So by looking at the red, green, and purple, I go over to my graph, and the falling weight deflectometer data from the red, green, and purple are all above 650,000. Matter of fact, averaging closer to about 725,000, as compared to 400,000. Sorry, this is in PSI. Looking at 400,000 PSI on the regular mat. I have been told all my life that if I were to look at the modulus of standard pavement, it is 400,000 PSI. So this yellow, which really, I guess I should have made orange on this, is representative of these two lanes here, which is non-fiber, except maybe an inch or 25 millimeters in the top, as compared to the intersections, which are full depth fiber. Now, what that relates to is there you're seeing quite an increase in modulus. Matter of fact, you begin to look at this, you're looking at a 50 to 75% increase in modulus. That does not translate that to a structural number. In the world of structure, it represents about a 20% improvement in structure, or moving from about a 5.3 total structure of the asphalt, that is, up to a 6.4, 6.2, 6.6. So an average of 6.4. That gives me confidence as a designer and measurable data, as I've seen not only on this, but other areas that we've measured for surface tech, that this validates. We talked about earlier about the high wrap. We talked about polymer replacement. In this case, what I'm doing is I'm using it to improve the structure of the pavement to protect the subgrade. The polymer replacement is one that gets to be a little easier, actually. What I'm doing here is I begin to look at, and it's not necessarily direct polymer replacement. I like to think more of it as a balanced mix design substitute. So, and I give you the for instance here, if my standard mixture is this gray dot and this blue dot and this green dot, which is a 70 minus 22, that actually should have a little bit of polymer in it. These are my standard mixtures. And my goal in balanced mix design, if you look at this graph, the bottom is rut resistance. Now, RRI is a calculated value where you multiply the cycles times 1 minus the rut depth. Actually, it's that's assuming 1 inch. If you're doing it in millimeters, naturally it'd be 25 millimeters times that, less that. What I do here is that helps me to normalize my rutting data. So a higher RRI is good. Where our mixtures are in the US, we tend to be in this lower right corner, which has really poor cracking resistance, but good rutting resistance. Well, if I go over and look at my vertical axis, my y-axis, this is giving my CT index. And like in the state of Kentucky, we're operating at about the 50 range when we need to be much higher than that to reduce cracking. If I go to the extreme and I have high cracking resistance, but poor rutting resistance, then I have a mixture that is real similar to what we had in the 80s. A lot of round rock, a lot of asphalt in it. Didn't crack, but it would rut and push. Rarely do you see poor rutting and poor cracking, and while we don't see those mixtures, they could exist. So what we want to do is we have most around the world, we're in this area here, and we need to move into this area. Like I said, I had a 6422 with one binder source, a 6422 with another binder source. And these are good numbers, by the way, as I'm moving up into, and I picked an arbitrary number. I said I want to be above 10,000 RRI, rut resistance index, and I want to be above a 100 on my CT index for this area. Notice my green one with the 7022 falls out. It is better in rutting, but it actually hurt me a little bit in cracking until I go and put aramid fiber in, and what the fiber does is take me straight north. Usually what fiber will do is move you up quickly and a little bit to the right. So the way I like to describe fiber is when we say it helps my cracking resistance and a little bit on rutting. And so if my goal is to move up and to the right, that's exactly what aramid fiber is doing. And that's how it works. And as long as I can do that, if I could do that with bubble gum, chewing gum, whatever it may be that I can put in my binder that would help me do this. In this case, I'm not going to use polymer. I'm going to use an aramid fiber. And actually in the very specific one, I used a little bit of polymer with aramid fiber to get the double effect. And now I'm pushing up near 225 cracking resistance. This mixture would be considered a superior mixture to put down. And I think what you're going to find out is in the next few years, instead of setting our goal just to barely move into this box, we're going to be challenged that our mixtures that are lasting 7 to 10 years, because of EPDs, because of the reduction of construction cycles, it's not going to be tolerable to go in there and every 10 years replace. They're going to be looking at higher values, much higher values than what we're aiming for today. This will be the tool to do that with. Dixie Highway is a project where they actually did the polymer replacement and looked at it. A lot of detail on this. They looked at reflective crack relief interlayers, multi-axial fiberglass mats. We're just going to look at the control, which is the no interlayer, but it's all 7622. And we're going to look at the aramid fibers that's added to the full depth lift. This is about 100 millimeters or 10 centimeters of an overlay. Today, what you're finding out as the cracks move through, it is cracking in the control lane. But when you look at the fiber lane, it's not cracking. Again, 4 to 5 inch or 100 to 125 millimeters overlay, depending on where you're at, over top of jointed PCC. What that looks like on a crack count is this. You have you have on your southbound lanes, which is your typical control. And we did look at some of the other treatments. The interlayer seems to be doing good. One of the grids look pretty good. The aramid fiber is looking among the best. But again, comparing just the aramid fiber today, this is the control at 622 feet of cracking in about, and sorry again, I'm in imperial units, in about 1,000 feet of pavement compared to 282. So half, 55% in the same distance, in the same 1,000 feet. So again, in the same amount of time and in the same distance, you have half the cracking. That gets back to what we talked about over to here. That is what we should be doing. When you add the fiber, it reduces cracking. And this is actually in Kentucky. This is outside of Louisville, a heavy traffic 4-lane roadway. Another one that was done is in the town of Plainfield, Indiana on Stafford Road. This is a 2-inch overlay. A contractor up there put this down for the city, and they wanted to look at polymer, the ACE XP polymer fiber, as compared to a 7622. And so what you're looking at on this, the control lane has 7622, and this has 7622 with aramid fiber in it. They did a lot of coring, a lot of investigation on this. Notice the cracks in the control lane. Notice what's going on here. Now, again, you can go and compare any of it. So I'd love to do a long view of this. Look at all the cracks that you see here as compared to what you see here. Again, the cracks versus no cracks. Now, as I began to look at it, that was about I think this was about a year. I think right at 10 months after the project. So what's it look like in the past few years? Well, in 2022, it was monitored. Now I'm going to get to our more current data. But when we looked at it, again, you can see there all the cracks in the control. And in the ACE XP polymer fiber lane, you do see some cracking, but nowhere near as severe as what's in the control. Well, what's that like when I put it together? Please focus on the left right now. On the left graph is your control, the 7622, and this is over time, looking from 2018 over to 2023. And this is in Indiana, it gets all 4 seasons and quite a bit of snow. In this one, again, in the empirical units, you have over 300 feet of cracking as compared to the same roadway, same time, but just putting in the polymer fiber, you're looking at only about 25 feet of cracking, linear feet of cracking per 1,000 feet. So again, 350 and 1,000 compared to about 25. Unbelievable. Again, the fiber is amazing by itself, but when you combine it with the polymer, you get next level. So you can use it to replace polymer or to complement polymer. To add to this, the project was also checked with an SCB. An SCB is also very similar to what we do with ideal CT, except it's a factor of 10 difference. In this case, a higher number would be better. So it was predicted, the Heritage Group actually ran this data, and when they took the samples, they found that the polymer fiber, the aramid fiber mix, had about a 12.41 index in the SCB IFIT, as compared to only about an 8.6. Well, today, how does that correlate? Here is your 8.6, which had the least cracking resistance, as compared to something that had quite a bit more, about 50% more cracking resistance. And sure enough, look what it did. Bluegrass Parkway is another one. While I don't have a lot of data on this, this is just a construction picture. And that is not fiber on the roadway. That's actually where they just did some grass cutting. And then what it looks like as of 2023. Again, beautiful roadway, some cracking, but very little compared to what Kentucky would see. So let me summarize all of this that we're talking about now into the bat vision and pavement distress. So again, what we do is we do a data collection through a video analysis, and we can actually take that image and flatten it, or we can do a top-down picture. We're also doing a 360. We put it into the software. We're able to pull images every 5 feet. So every 5 feet, or about every 1.5 meters, we're pulling an image off the roadway, full width image. We take that, run it through the artificial intelligence, and it begins to predict the type, like block cracking, and by reverse imaging and being able to understand and get a better picture, it's able to understand this is not just a regular crack, this is a block crack, or this is a reflector crack. This is a pothole. This may be not a pothole, this is a manhole cover. This software can even inventory street lights, curb and gutter, but in this case, we've got it trained to look at things such as rutting, cracking, edge cracking, longitudinal cracking. And then we come up with a visualization tool. So we did that. We went out and scanned the roadways, and you can see the camera system that's set up. We took this. Again, we're looking at the type of cracking that we find. Then we go through this imaging to understand the severity of it. And then by using this type of other thing we can do is we can also get the ride profile if we need to from all of this. This is an example of what the data would look like. This is just an example of in Missouri. Jefferson City uses this technology, and we can get all the different types of cracking. We can get the pavement condition index, and all the different sections and street type, and then what type of classification they are. These are not fiber projects. This is just a demonstration of software. Now let's look at what the fiber has done. 2023, BAT was contracted to survey the aramid fiber projects in Kentucky and Indiana. As we did that, we began to develop these dashboards, just like what we did with other projects. This is looking at the Beckley Road part. What we found out on this project, Beckley Station Road had a 74 in the control compared to an 80 and an 85 where the fiber was. What's interesting is this one that's worse, the control, was paved a year later, so it's actually newer. What is the primary mode of cracking in all of this? It is block cracking, followed by some type of joint or edge cracking, followed by some raveling. And these are your major distress is 1.36 severity of block cracking. To achieve, if you look at the average, let's call it, we'll go on the low side, let's call it an 82 on average compared to a 74. To receive an 8-point improvement on a PCI value is the difference in this one being non-treatable to this one needs maintenance. Okay, this one's good. This one needs maintenance. These projects, I think, were placed in 2016. So you're looking at something that's about 7 years old. This one's doing fine. Again, the control needs to be replaced, and the control is only 6 years old. This is Stafford, Indiana. This is Indianapolis Airport sitting right into here, and this is the Plainfield Road that we looked at. In this case, we looked at the fiber section, and this is the fiber east and west, an average of 89 compared to the control, which would have an average of 84.5, just call it 85. So again, you have a 5-point difference of an 85 compared to an 89. Why isn't it much more than that? Well, it's because it's only light transverse cracking. Transverse cracking will turn into block cracking. Block cracking becomes more severe. These numbers will begin to spread more. And this is Stafford Road that we just looked at, where that had a significant difference on the extent. Severity, not as much. On the extent, it was quite a bit. Again, we're looking at an overall, not just a cracking index, but we're looking at all the types and the raveling and the bleeding and alligator cracking. Overall, we have a 5-point improvement on PCI. When these numbers go on down, you're going to find out that this one may need treatment in about 1 to 2 years, where this one is considered excellent condition. We're going to continue to monitor this on an annual basis. We also looked at Mercer Road. Mercer Road, just to remind you what it was, that was the high wrap, or this is the rearm project that Surface Tech did. Funny enough, the road that has 20, it says 25% wrap. The road that has 20 to 25% wrap has an 89. It has dropped now to an 89, still doing very well, as compared to the 45% wrap with fiber and bio oil that is performing at 96. Matter of fact, if you look back on all of these, one of the best, and again, it's the newer one, but the best performing one so far is the high wrap. So can we use high wrap and do it responsibly? Absolutely. And the contractor that did this had excellent wrap management going on that day. I show you this on the bottom to let you see the dots, and this shows you the amount of data collection. And if I had this active, you can actually click on this and look at the pictures and drive the roadway to look at each distress type that it's measuring. In summary, Beckley Station, you're looking at a control of 74 compared to an 80 and 85. Dixie Highway, you're looking at a control of, and this is over reflective cracking. So a caveat on this one is that you're fighting a losing battle because you're over top of concrete. However, what did it do? And if you look at the time, it did very well. And now it's starting to catch up and all the joints are starting to reflect through. But you're looking at an 83, 84 compared to an 81, 85. The average, this one eases out a little better on the average, but for all intents purposes, just call them the same. Mercer Road, and Mercer Road, we're looking at an 89 versus 96 with fiber. Stafford Lane, 84, 85 versus 88, 89, a 5% improvement as compared to 7 on the one above. Man of War, that's the one where we did the full depth structural replacement. And that one we are looking at, where it's a polymer type replacement. This one, everything is performing among the best at a 92. Overall, Aramid fiber, in everything that we're looking at so far, coming off the data, looking at the live projects that we have in Kentucky and Indiana, which is a neighboring state to Kentucky, we're seeing improvements in rutting in the laboratory, in the lab and in the field. We're seeing improvements in cracking and fatigue, improvement in structure, improvement in modulus. The best part is no change in the JMF. And again, if you need to see it, seeing is believing. It's easy to find out that it's in your mix. With that, that is the end, George, and thank you for allowing me to be able to walk you through this today. And I hope this was useful.
Yeah, I think that's really good, Phil.
It's quite a bit.
I did cross.
It's a lot of data.
Yeah, no, that's really good. I think I did cross my mind as we're going through that presentation you've just done would have probably actually almost been better for every bit I did last week or the week before.
Yeah.
But that's all right. That's cool. I think that's really good.
No. Well, this one's really meant to be, if I focused on this one, and I do have aspects of this one in the other one. The other one teaches more about aramid fiber. This one is focused on the end result, but this one's for my mature audience.
Yeah, exactly.
Rated M for mature.
Yeah, good. So, well, if you're happy, I might recording off now. So I might